Welcome back. In this video, we're going to talk about the key ideas behind techniques for recognizing handles. There is good news and bad news when it comes to recognizing handles. The bad news is that there is no known efficient algorithms that recognizes handles in general. So for an arbitrary grammar, we don't have a fast way to find the handles when we're parsing. The good news is that there are heuristics for guessing handles, and for some context-free grammars, for some fairly large classes of context-free grammars, these heuristics always identify the handles correctly. We can illustrate the situation with a Venn diagram. If we start with a set of all context-free grammars, then the unambiguous context-free grammars are a subset of those, and then an even smaller set are what are called the LRK grammars. And here, just to remind you, L stands for left to right scan, R stands for rightmost derivation, and K stands for the number of tokens of look ahead. Now, the LRK grammars are one of the most general deterministic families of deterministic grammars that we know of, but those aren't the ones that are actually used in practice. Most of the bottom-up tools that are practical use what are called the LALRK grammars, which are a subset of the LRK grammars. And then what we're going to talk mostly about is a simplification of those called the simple LR grammars, or the SLRK context-free grammars. And these containment relationships are strict. That is, there are grammars that are LALRK, but not SLRK for every K. And similarly, there are grammars that are LRK for every K that are not LALRK. As we've already said, it's not obvious how to detect handles. So what does the parser know? Well, it sees the stack. At each step, it knows the stack that it has already constructed. And so let's see how much progress we can make just thinking about what information we can get from the stack. So here's the definition. We're going to say that alpha is a viable prefix if there is some omega such that alpha bar omega is a configuration, a valid configuration of a shift-reduced parse. Now keep in mind that the alpha here, this is the stack, and the omega here is the rest of the input. And what does that mean? That means the parser knows this part. The parser knows alpha. It doesn't know much of omega. It can do some look ahead. It can look at a small prefix of omega, usually just one token, but it certainly doesn't know the whole thing. So what does a viable prefix mean? Well, a viable prefix is a string that does not extend past the right end of the handle, and the reason we call it a viable prefix is because it is a prefix of the handle. So as long as the parser has viable prefixes on the stack, no parsing error has been detected. And really, the definition is just giving a name to something. It's not anything very deep. The fact that alpha bar omega is viable, that's just saying that we haven't encountered an error, that this is some state of a shift-reduced parse. It hasn't said yet how we're going to identify it or anything like that. It's just saying that these are the valid states of a shift-reduced parse. Now, the definition is useful in one way, which it brings us to the last important fact number 3 about bottom-up parsing. And that's that for any grammar, the set of viable prefixes is a regular language. And this is really an amazing fact, and one that's going to take us a little while to demonstrate. But this is the key to bottom-up parsing. At least all the bottom-up parsing tools are based on this fact, that the set of viable prefix can be recognized by a finite automaton. So we're going to show how to compute this automaton that accepts the viable prefixes, but first we're going to need a number of additional definitions. The first definition we need is the idea of an item. Now, an item is a production that just has a dot somewhere on the right-hand side. So here's an example. Let's take the production T goes to open paren, E close paren. What we're going to do is we're just going to put a dot in every possible position on the right-hand side. So we'll have one item where the dot is all the way at the left end. We'll have one where the dot is all the way at the right end. And then we'll have items where the dot is between every pair of consecutive symbols. So in this case, there are 4 items for the production. One special case is what do we do with epsilon productions? Well, for an epsilon production, there are no symbols on the right-hand side. We'll just say there is one item, x goes to dot. And these items, you'll see them referred to if you look in help pages and in the literature as the LR0 items. Now we're ready to discuss how we recognize viable prefixes. And the problem is that the stack has only bits and pieces of the right-hand sides of productions in general. Most of the time, we don't have a complete right-hand side on top of the stack. Most of the time, we only have a part of a right-hand side. And it turns out that what is on the stack is actually not just random. It actually has a very special structure. And these bits and pieces are always prefixes of right-hand sides of productions. That is, in any successful parse, what is on the stack always has to be a prefix of the right-hand side of some production or productions. Let's take a look at an example. Let's consider the input open paren, int, close paren, and here's one of our favorite grammars. Now, this configuration where I have open paren e on the stack, remember that this is our stack, and we have the close paren in the input. This is actually a state or a valid state of a shift-reduced parse. And you can see here that open paren e is a prefix of the production. T goes to open paren e, close paren. And after we shift the remaining close paren onto the stack, then we'll have the complete right-hand side and we'll be ready to reduce. So this is where the items come in. The item T goes to open paren e dot close paren. This describes this state of affairs. It says that so far we have seen open paren e of this production, and we're hoping in the future to see the close paren. So another way of thinking about it is that this item records the fact that we're working on this production, and that so far we've seen this much. Everything to the left of the dot is what we've already seen and is what is on the stack. And what is to the right of the dot is what we're waiting to see before we could possibly reduce. And we may or may not see that. Remember, the parser doesn't know the input. In this case, of course, it's the very next symbol, and so it can see it in the look ahead. But at this point in time, the parser doesn't know for sure what's coming up, and and if this dot were further to the left, there might be many, many more symbols that we had to go before we could perform the reduction. So anyway, what's to the left of the dot records what we've already seen, and what is to the right of the dot says what we're waiting to see on the stack before we can perform a reduction. And now we can talk about the structure of the stack. So as we said, it's not just arbitrary collections of symbols. In fact, it has this very particular structure. So the stack is actually a stack of prefixes of right-hand sides. So the stack always has this organization where there's a bunch of prefixes stacked up, literally stacked up on the stack. And what's going to happen is that the ith prefix, if we were to pick a prefix out of this stack of prefixes, well, that must be the prefix of some production, okay, the right-hand side of some production. And what that means is that that prefix, that ith prefix on the stack, will eventually reduce to the left-hand side of that production. So it'll eventually reduce to xi in this case. And then that xi has to be part of the missing suffix of the prefix that is below it on the stack. So if I look at the previous prefix, the one that's right below prefix sub I on the stack, then when I perform this reduction, that xi needs to extend that prefix to be closer to a complete right-hand side of that particular production. Okay? So in particular, there's going to be some production that is going to already have a portion of its right-hand side on the stack, so prefix sub I minus 1, and xi is going to extend that prefix. And then there's going to be some more stuff possibly that we're waiting to see even after the xi is put there. And recursively, all the prefixes above prefix k eventually have to reduce to the missing part of the right-hand side of prefix k, the alpha k that goes on the right-hand side. All right, so I have this image that you have a stack of prefixes. We're always working on the topmost prefix on the stack. So we'll always be working here at the right end, shifting and reducing. But every time we perform a reduction, that has to extend the prefix immediately below it on the stack. And when a bunch of prefixes have been removed from the stack through reductions, then we get to work on the prefixes that are lower in the stack. So let's illustrate this idea with an example. So here is another input string. We're going to use the same grammar. You can rewind if you want to see the grammar again. But let's consider this state where we have open paren int star on the stack, and we have int close paren remaining in the input. Okay, and so what items would record? What is the stack structure here, and how do the items record it? Well, let's start here at the bottom. Let's actually work from the bottom up. So we have int star at the top of our stack. So this is the right-hand side that we're currently working on, and that would be a prefix of this production. T goes to int star t. Okay, so what this says is that we're looking. We've seen int star so far, and we're waiting to see t. Now, I'm not showing the items, but I'm just showing the productions that this is eventually going to use. Now, the one that's below it here, the prefix that's below it on the stack, is right here in between the open paren and the int. This one's an interesting case. It's actually epsilon, so there's nothing there now on the stack. But eventually, once the int star has reduced to t, okay, then that t is going to reduce to e. And currently, of course, there's not a t there at all, so we've only seen epsilon. We've seen none of the prefix of this production on the stack. And then for the last production, the one deepest in the stack, we've currently seen an open paren, and we think we're working on this production. T goes to open paren, e close paren. All right, and so when this e is produced, that will extend this right-hand side. And now we can record all of this with the stack of items. T goes to open paren dot e, e goes to dot t, and t goes to int star dot t. Okay, and it just records what we said on the previous slide, that so far we've seen the open paren of this production, we've seen nothing yet of the right-hand side of this production, and we've seen int star so far of this production. And just notice how the left-hand side of each of these productions is going to eventually become part of the right-hand side of the right-hand side of the production we're working on, just below it in the stack. So when we've reduced this int star t to t, that will extend to this production, and when that reduces to e, that will extend this production. To summarize this video, we can say a little more precisely how we go about recognizing viable prefixes. The crux of the problem is going to be to recognize a sequence of partial right-hand sides of productions where each of those partial right-hand sides can eventually reduce to part of the missing suffix of its predecessor. Next time, in the next video, we're going to actually give the algorithm for implementing this idea.